लास्ट टाइम क्या कर रहे थे हम लोग? लास्ट टाइम क्या किया था? बताओ भाई, कोई तो बताओ। वर्क डन बाय स्प्रिंग कब किया था? ठीक है. So today we are going to talk about the work energy theorem. And this is like I told you, I think in the last class, and this is the last tool that we will have for the analysis of motion of a point particle. And using the tools that we have learned up till now, including kinematics, dynamics, what we will be doing is that we will be extending in the next chapter these tools so that they are applicable for a collection of point particles. Okay? So still, if I give you a problem which contains a collection of point particles, then it is possible that you will not be able to solve it because we do not know how to apply uh, Newton's laws of motion and work energy theorem on a system of point particles. So all the things that we have discussed up till now is applicable on individual point particles. You cannot construct a system in which there are two objects and these two objects are moving with separate accelerations. If they have the same acceleration, then there is no problem. Then you can consider the whole thing as one big object. Okay. So the work energy theorem tells us that the summation of work done on an object is equal to change in kinetic energy of the object. Right? अब ये आ कहाँ से रहा है? यहाँ पे इसका मैं डेरिवेशन दिखा देता हूँ. So very weird. The concept of the work energy theorem is actually coming from Newton's second law of motion. This is basically a restatement of the second law, but एक minute. स्मिथ, तेरे को अभी टाइम मिल रहा है आने का. हाँ, उससे पूछना मत कि इससे पहले क्या हुआ, इसके बाद क्या हुआ. डेरिवेशन इसका मैं दिखा रहा हूँ. So we know that F is equal to ma, and I can write F as m dv by dt is equal to, so F is equal to m dv by dt, and if you remember, I can multiply and divide by the same object, उससे कोई फर्क नहीं पड़ेगा. So now I will write this as m into dx by dt into dv by dx. But dx by dt, remember, is v, right? ये हम पहले भी कर चुके हैं. So this is mv dv by dx, and then I take dx on this side and I write this as equal to mvdv and I integrate this. This integration is done from some initial velocity to some final velocity. So I get half mvf square minus half mvi square. Right. So what we do is we define work as the LHS, which is integral f dx, and RHS we get the kinetic energy, and you all know पहले से पढ़ा हुआ है that kinetic energy is equal to half mv. Kinetic energy आ कहाँ से रहा है? Where is this kinetic energy coming from? This kinetic energy is coming from the integration of mv. So I'm assuming that mass is constant. Okay, and since we are talking about a point particle, this is a good assumption. So work done on an object is equal to the change in kinetic energy of the object. Okay. Now, again, first weird thing to notice is that this is just a restatement of f is equal to ma. Right? So f is equal to ma written in a different way. क्या किया मैंने? a को v dv by dx लिखा, dx को मैं क्रॉस मल्टीप्लाई करके लेफ्ट हैंड साइड में ले गया और दोनों तरफ इंटीग्रेट कर दिया. तो इंटीग्रल एफ dx जो LHS में आया उसको मैंने बोला कि अच्छा चलो इसको ना एक नया टर्म डिफाइन करते हैं जिसको हम बोलेंगे वर्क. और RHS में जब मैंने m को बाहर ले लिया बिकॉज m इज कांस्टेंट, तो इंटीग्रल v dv आया. राइट. एंड इंटीग्रल v dv वुड बी v स्क्वायर बाय 2. उसमें मैंने लिमिट्स डाले vi और vf, इनिशियल फाइनल वेलोसिटी के लिमिट्स डाले जब मैंने, तो मेरे पास आया हाफ mvf स्क्वायर माइनस हाफ mvi स्क्वायर. तो ये हाफ mv स्क्वायर को मैंने बोला लेट्स डिफाइन दिस गाय as a thing called kinetic energy. Okay. तो ये मेरा work energy theorem is basically a restatement or another way of writing f is equal to ma. It tells me that the total work done on a point object must be equal to the change in kinetic energy of that point object. Okay. What would happen if I have a system of point objects? Right? So the second weird thing is that for a system of objects, so the second weird thing is that Newton's laws of motion, F is equal to ma, this guy, you cannot apply on a system in which there are two or more objects which are having different acceleration. Right? I hope this is clear to everyone. I'll just show you on a new slide. If I give you a problem like this, and I have given you a problem like this, if I give you a problem like this, and I ask, please tell me the acceleration of the wedge, right? We have already done this problem. You cannot say that, look, I will choose this as the system, and I will apply F is equal to ma on this system. This would be wrong. It would be wrong, or let me not use the word wrong. Let me use the word useless. So this will be useless. I haven't taught you, we have not discussed as yet how to apply F is equal to ma on a system comprising of two or more objects where the objects have separate acceleration. If, on the other hand, I give you a problem like this, which again we have already discussed, if I give you a problem like this and I say find the acceleration, and you take this guy as the system, and then you write F is equal to ma for the system, then this is useful, okay? Because all the three have the same acceleration. Here it is useful for you, here it is useless for us. But the work energy theorem, okay? The work energy theorem, which is just a rehash of F is equal to ma, apparently has no reservations, apparently has no problems in application on a collection of point objects. Right? So for a system of objects, summation of work done on object 1 plus summation of work done on object 2 and so on is equal to change in kinetic energy of object 1 plus the change in kinetic energy of object 2 and so on. Okay? So all you do is apply the work energy theorem individually, and you add everything up, and uh, that gives you the work energy theorem for a system of objects. Okay? So generally, what I'm going to write down, generally, summation of work done total is equal to change in kinetic, right? मैं total लिख दूं या for all objects लिख दूं, सबसे ठीक है. Okay, लिख लिया ये. I hope everybody is written this. Please write this down. हाँ, उसके बारे में ज़्यादा नहीं सोचना है अभिजीत. एफ और एक्स के बारे में ज़्यादा नहीं सोचना है. मैंने आपको वर्क डन का एक और डेफिनेशन बताया हुआ है, विच इज सुपीरियर टू दिस, क्योंकि ये मैंने 1 डायमेंशन में यूज किया ना. हम 3 डायमेंशन में भी वर्क डन का डेफिनेशन देख चुके हैं. That is the line integral of force. लिख लिया सबने? Okay, so here work energy theorem is applicable. Here also work energy theorem is applicable, no problems. Okay? Sure. So let me tell you the steps. So how to apply work energy theorem on an object or on a collection of objects. हाँ स्मिथ, बिल्कुल सही है। वर्क एनर्जी थ्योरम में सारे फोर्सेस का समेशन होता है या सिर्फ कंजर्वेटिव? सारे फोर्सेस का, सारे। हाँ हाँ, पार्थ, पार्थ ही तो बोल रहा हूँ। So how to apply the work energy theorem on an object or a collection of objects? Well, you remember that I started this chapter by teaching you the line integral. And when we discussed what the work done due to different forces are, right, we applied the line integral to find out the work done, but the final expressions for work done were very, very simple, right? So just like I discussed in the last class also, you are using this device in which you are watching, in which you are listening to me, how the device works, what are the inner working of the device, you don't really care. Okay? आपको ये मालूम है कि आप एक बटन, जूम का बटन दबाओगे और कुछ उसमें डेटा फीड करोगे, लॉगिन करोगे, मीटिंग आईडी दोगे, तो आपको ये सामने दिखाई देगा, राइट? So in the same way, when we are applying work energy theorem, we will not bother ourselves with the definition of line integral. लाइन इंटीग्रल कैसे निकाला जाता है ये मेरे को पता है या नहीं पता है, उससे जब वर्क एनर्जी थ्योरम का एप्लीकेशन हो रहा है तो मुझे कोई मतलब नहीं, राइट? अनलेस ऑफ कोर्स वो चीज आ जाए जो अभी तक मैंने डिस्कस नहीं किया है, दैट इज वर्क डन बाय एक्सटर्नल एजेंट्स, विच इज कॉम्प्लिकेटेड। सिंपल वर्क डन है, एक आदमी एक बक्से को खींच रहा है, कोई प्रॉब्लम नहीं है, दैट यू कैन फाइंड आउट। So unless and until we have some further complication, which I will explain later, we are not supposed to remember the line integral method. We are only supposed to remember the final expressions for work done due to various forces. For example, the work done due to gravity is equal to plus minus mgh, where h is the vertical distance between the initial and final points. Okay? Work done by normal reaction is 0. Work done by tension is 0. Work done by friction is plus minus mu mg into horizontal distance. Okay? Of course, this is there with certain conditions which also we have to remember. And then work done by spring is equal to half k xi square minus xf square, right? तो ये फाइनल एक्सप्रेशंस हमें याद रखने हैं, अंदर का जो चीज है वो हमें याद नहीं रखना है। लाइन इंटीग्रल कैसे डिफाइन होता है वो हमें याद नहीं रखना, ठीक है ना? एक so we are not supposed to worry about the line integral when applying work energy theorem, right? For now, as of now. However, the prerequisites I told you about the line integral, they are important, right? What are the prerequisites I told you about calculation of the line integral? क्या तीन चीजें मालूम होनी चाहिए अगर आपको लाइन इंटीग्रल कैलकुलेट करना है एक वेक्टर फंक्शन का? So you should remember, or you should be given the vector function itself, which in this case is the force. तो लाइन इंटीग्रल कैलकुलेट करने के लिए आपको फोर्स की जानकारी होनी चाहिए। दूसरा, आपको इनिशियल पोजीशन और फाइनल पोजीशन की जानकारी होनी चाहिए। और तीसरा, आपको पाथ की जानकारी होनी चाहिए, राइट? सो यू शुड हैव थ्री पीसेस ऑफ इंफॉर्मेशन विथ यू to evaluate a line integral. Now remember, how to evaluate, we don't care at the moment. I'm just asking you to remember the prerequisites of carrying out a line integral. Three prerequisites. Number one, you should know the force vector F. Number two, you should know the initial and final points. And number three, you should know the path that the particle has taken. So how are we going to interpret these three mathematical conditions here in mechanics? Like, it's simple. First, force पता होना चाहिए। इसका इंटरप्रिटेशन ये है कि ऑब्वियसली ये है कि एक ऑब्जेक्ट के ऊपर कौन कितनी फोर्स लगा रहा है, ये आपको पता होना चाहिए। यू शुड नो व्हाट इज द फोर्स बीइंग अप्लाइड ऑन द ऑब्जेक्ट, राइट? Second, you should know the initial and final configuration of the object. Right? This is very, very important. You should know the initial and final configuration of the system, or you should know the initial and final position of the object जिसके ऊपर आप वर्क एनर्जी थ्योरम लगा रहे हैं। अगर आपको उस ऑब्जेक्ट का इनिशियल फाइनल पोजीशन नहीं मालूम है तो आप वर्क एनर्जी थ्योरम नहीं अप्लाई कर सकते, राइट? दिस मेक्स सेंस because work done by earth is mgh, where h is the vertical distance between the initial and final position. So if you don't know where the particle was initially and where the particle is finally, there is no way that you are going to apply mgh, right? You will never be able to find h. And the third thing that you must know is what is the path taken by the particle, right? So let me repeat. Number one, you should know what is the initial and final configuration of the system, or you should know the initial and final location of the particle. Now, why am I using two separate sentences here? Why am I saying configuration of the system, then I'm saying position of the particle? Well, a system consists of more than one point particle. So when I say that you should know the initial and final configuration of the system, what I mean is that you must know कि उस सिस्टम में सारे पार्टिकल्स इनिशियली किधर थे और सारे पार्टिकल्स फाइनली किधर, राइट? सो फॉर एग्जांपल, वी हैव एन एटवुड मशीन। एटवुड मशीन में दो ब्लॉक्स, मैंने दो ब्लॉक्स को रिलीज कर दिया और कुछ देर बाद मैंने पूछा कि अच्छा बताओ, जैसे लास्ट टाइम आपने वर्कआउट किया था, व्हाट इज द वर्क डन बाय टेंशन ऑन द इंडिविजुअल ब्लॉक्स ऑफ द एटवुड मशीन। सो यू शुड नो कि ये सिस्टम में ये जो दो ब्लॉक्स थे पहले कहाँ थे और बाद में कहाँ हैं, राइट? तो द फर्स्ट prerequisite, the first step number one, find the initial, final configuration of the system. Step 2, as the system moves from the initial to final configuration, find the forces acting on each object of system. Step 3. Find summation of work on all objects of the system. Step 4. Find initial kinetic energy, final kinetic energy of the whole system. Okay? And then, of course, you will apply summation W is equal to. Please write this down. Please write this down quickly, and then I'll show you how to apply these steps. अब अथर मैं तुझसे पूछूं तेरा नाम क्या है और बोले it starts with A sir. My name starts with A. फिर मैं तेरा नाम बता दूंगा. क्यों? बताओ भाई. बताओ अथर. If you tell me, हाँ मैं फिर से बोल रहा हूँ. If I ask you your name and you tell me that your name starts with A, can I tell your name? Exactly. So, if only one piece of information is given, then you will not be able to do anything with it. Okay? It's just like me telling you my name starts with a K. अब आप guess करते रहो क्या है, कोई मतलब नहीं है ना. All pieces of information should be there, otherwise you will not be able to apply the work energy. Not one, all. लिख लिया सबने, आगे बढ़ूं मैं. I want to show you how to do this. Can I change the slide? Hello, hello, hello. Okay. So now, supposing that I give you a question where I tell you this is 2 kg, this is 3, 3 kg. Find velocity of 2 blocks after they have traveled a distance of 1 meter after release from rest. Yeah. Now, so how will I do this problem if I did not know work energy theorem? Well, I will say that this is an Atwood machine, so I know the acceleration of the 2 blocks. I will figure out the acceleration of the 2 blocks, and then since the acceleration will come out to be constant, and since the initial velocity is given to me as 0, I will simply apply the kinematic equations of constant acceleration. V square is equal to u square plus 2as. I have worked out using Newton's laws. S is given to me, U is given to me, and therefore I will be able to work out the value of V. Okay? So I want to show you how I will work out the value of V. I will apply the work energy theorem to work out the value of V. Okay? So please remember that this is an example to showcase how the steps are applied. इसके बाद जो मैं प्रॉब्लम दूंगा that will be more complicated, but whatever steps I am following here, the same steps will be followed there as well. Okay, so let's see what the steps are first. First step, find the initial and final configuration of the system. Okay. Find the initial and final configuration of the system. इसका मतलब क्या है? What are the implications here? Well, the implications are very weird. You see, if I ask you to apply Newton's laws of motion, F is equal to ma, then all you have to do is draw the free body diagram of the object or objects. That's it. You don't care, or at least Newton's laws do not care where the object is coming from and where it is going. You are only interested in the fact that you have drawn the free body diagram of the object or objects at a particular moment in time. And you should be knowing that, look, this free body diagram does not change with time. तो अगर मैं इस केस में ये ऊपर वाले ब्लॉक का एफबीडी बना रहा हूँ, राइट, अगर मैं इस केस में इसका एफबीडी बना रहा हूँ, तो इसका जो एफबीडी होगा वो ये ब्लॉक ऊपर रहेगा इंक्लाइन पे या नीचे रहेगा इंक्लाइन पे, एफबीडी हमेशा सेम रहेगा. So Newton's laws of motion F is equal to ma is applied on any instantaneous configuration of the system, whereas for the application of work energy theorem, you need to know the whole, the whole journey of the system. The work energy theorem is applied between 2 points on the journey of the system. So if I release the Atwood machine in this position from rest, right, and I have asked something about something after they have traveled a distance of 1 meters. This means that the 3 kg block is here and the 2 kg block is here, where this distance is 1 meter, and of course this distance is 1 meter. I'm sorry about my diagram. दोनों distances अलग दिखाई दे रहे हैं, but है. So the 2 kg block has gone up, the 3 kg block has gone down by 1 meter. So the black thing represents the initial configuration of the system, whereas the blue thing represents the final configuration of the system. Bhavya, it is not, see, answer you can find out. I can give you another question, जो आप answer नहीं निकाल पाओगे, right? So what is more important here is to understand the philosophy behind the question, right? So please pay attention on that. So here I have found the initial and final configuration of the system. पहले ये blocks कहाँ थे, अब ये blocks कहाँ हैं? Okay, and please also notice that I have a system consisting of 2 blocks, 2-point objects. Problems that I am going to give you will have either a single point object as the system, or will have 2, just like the example shown, may have 3, may have more. Okay. Generally, it is going to be 1, sometimes 2, 3, very rarely more than 3. So I have figured out the initial and final configuration of the system. Very, very important. Okay, that is why I am stressing on it. अगर आपके सामने एक प्रॉब्लम आती है, वर्क एनर्जी थ्योरम अप्लाई करना है, कब अप्लाई करना है ये भी मैं अभी बता दूंगा. वर्क एनर्जी थ्योरम अप्लाई करना है तो आपको उस सिस्टम का इनिशियल और फाइनल कॉन्फ़िगरेशन मालूम होना चाहिए, और वो इनिशियल कॉन्फ़िगरेशन से फाइनल कॉन्फ़िगरेशन कैसे पहुंचा ये भी मालूम होना चाहिए. इस केस में बहुत ही ऑब्वियस है कि 3 किलोग्राम वाला ब्लॉक स्ट्रेट लाइन में ट्रैवल किया, 2 किलोग्राम वाला ब्लॉक स्ट्रेट लाइन में ट्रैवल किया. उसके बाद से व्हाट इज द सेकंड स्टेप हियर? As the system moves from the initial to the final configuration, find the forces acting on each object of the system. इसका क्या मतलब है, right? Please try to understand the statement, not only in the context of this problem. This is just an example. This is a very easy example. You can do it in 2 seconds, 2 minutes. कोई problem नहीं. Understand what am I saying? As the system moves from the initial to the final configuration, you must have the knowledge of the forces acting on the various objects within the system as the system moves from its initial to final configuration. Now here there is no ambiguity. As these 2 blocks move from the black position to the blue position, the forces acting on both the blocks are gravity and tension, और कोई force नहीं. Furthermore, these forces are acting throughout the motion of the object. So I am going to give you a question where there will be forces only for part of the motion of the object. Right? This is going to be there. This is going to be a common feature. एक ऑब्जेक्ट इनिशियल से फाइनल पोजीशन गया, आधे रास्ते फ्रिक्शनलेस था, आधे रास्ते में फ्रिक्शन था. तो फॉर पार्ट ऑफ द मोशन ऑफ द ऑब्जेक्ट, फॉर पार्ट ऑफ द पाथ ऑफ द ऑब्जेक्ट, फ्रिक्शन इज एक्टिंग ऑन इट. Okay, right? So not only must you know the initial and final configuration of the system, you must also know the forces acting on the various objects of your chosen system, and whether these forces act throughout the motion of the system, or do they act only along only at a part of motion. Okay. Next step. Find the work done on all objects of the system. Let's do that. Find the work done on all objects of the system. This is how I prefer to do this. Summation W is equal to work done by gravity plus work done by tension. Okay, और तो कुछ है नहीं. तो वर्क डन बाय ग्रेविटी ऑन बोथ द ऑब्जेक्ट्स मेरे को निकालना है. वर्क डन बाय ग्रेविटी इज इक्वल टू प्लस 3g1. प्लस क्यों लिखा है? ये प्लस क्यों लिखा है? क्योंकि ये 3 किलोग्राम वाला ब्लॉक नीचे गया. प्लस mgh. This is the work done by gravity on the first block. Okay, minus 2g1. This is the work done by gravity on the second block. माइनस क्यों है? क्योंकि ये ऊपर गया है. into mass 2 into g into the displacement, into the vertical distance between the initial point and the final point. Okay? In fact, I like to write that this is the initial configuration of the system and this is the final configuration of the system. Okay? Plus, अब हमने देखा था लास्ट टाइम कि अगर इंडिविजुअल ब्लॉक्स पे हम टेंशन निकालेंगे, वर्क डन बाय टेंशन निकालेंगे, तो दैट विल कम आउट टू बी नॉन जीरो. बट वर्क डन बाय टेंशन ऑन बोथ द ऑब्जेक्ट्स, work done by tension on all the objects in the system is always zero, right? In fact, work energy theorem is invented to make work done by normal reaction and work done by tension equal to zero. So we don't have to bother about the constraint forces. So I have found the total work done, and that is equal to G, or 10 joules. Right? Please be very careful about the units. So I have figured out now the work done. Okay, summation W मैंने निकाल दिया. ये दोनों स्टेटमेंट्स मैंने अलग क्यों लिखे हैं? ऐसा भी हो सकता है कि मैं आपसे डिस्प्लेसमेंट पूछ लेता. वर्क डन तो इतना है, चेंज इन काइनेटिक एनर्जी इतनी है, अब मेरे को डिस्प्लेसमेंट बताओ. इन दैट केस 1 की जगह x आता, यहाँ पे 1 की जगह x आता. ओके, यहाँ पे 1 की जगह x आता, यहाँ पे 1 की जगह x आता, और यहाँ पे x आता, यहाँ पे x आता. So whenever you are finding the work, it does not mean that you know the work. Yeah, you may have to assume something. Something may be asked in the question. So you have to find out the work done. Yes. Do you know the value? Will you know the value of the work done? I can't say. That will depend on the question. Next, find the kinetic energy initial and kinetic energy final, right? So this is the reason why I have written it separately. So we get initial kinetic energy of the system, kinetic energy initial, this is equal to 0. Kinetic energy final is equal to half mv square plus half mv square. Now please understand that I know, okay, I know that the velocity of this guy and this guy will be same. I know that if at this position this is moving with this velocity, then this will be moving with this velocity. Okay, मैंने थोड़ा सा गलत statement बोल दिया. Velocities are not equal, speeds are equal. Right? Velocities are not equal, speeds are equal. So they are both moving with equal speed, and I have assumed that speed to be equal to. I have assumed that speed to be equal to v. Okay. Now I have worked out the final kinetic energy. I have worked out the initial kinetic energy. I have worked out the work done. So it's time to apply the work energy theorem. Summation of work done. Summation of work done is equal to change in kinetic energy, half into 3v square plus half into 2v square. 3 by 2 plus 1, right? So 10 is equal to 5 by 2v square. And this gives me v is equal to 2 meters per second. Right? 5 cancel हो जाएगा, 10 से 2 आ जाएगा, 2 into 2 4 हो जाएगा. V square is equal to 4, V is equal to 2. This is how you apply the work energy theory. Okay? So I will give you one question. I will give you one question. आगे बढ़ो. Should I change the slide? Can I change the slide? Please take a screenshot. हाँ सही है ना सर। शहीद क्या पूछ रहा है मुझे समझ में नहीं आ रहा। ओके, फर्स्ट स्टेप, इनिशियल एंड फाइनल, initial and final. Right. So up till this point, no forces act on it, and then from here to here, spring force acts on it. So summation W, we get work done by spring. Nothing else. If you want to be pedantic, then we can have work done by normal reaction. Work done by spring is half K initial elongation or compression square. Right now, if you look at the spring, then the spring has one end which is free, and if that is the case, then that means that necessarily the spring must have been before the block comes in contact with it. The spring must have been at its natural length. Therefore, the compression or the elongation of the spring initially must be zero, zero square. So since one end of spring is free initially, this means that xi is equal to 0 minus final compression whole square. Okay, now I don't know फाइनल कंप्रेशन कितना है, इनफैक्ट वही चीज तो निकालनी है मेरे को, मैक्सिमम कंप्रेशन निकालना है. So here I'll get x. Work done by normal reaction is 0. Right? हाँ सही बोल रहा है, बट उसके बाद से ब्लॉक जाके बढ़ जाएगा ना उससे. Initial kinetic energy of the block. Initial kinetic energy of the block is half mv naught square. Can anybody tell me what will be the final kinetic energy of the block? Can anybody? Very good, Abhijit. Yes, yes, Satyam. Good, good. So the final kinetic energy of the block will be 0. Okay, and this is very important. So the spring has maximum compression or elongation when both of its ends have the same velocity. So if this end of the spring is fixed, this end has 0 velocity. Maximum compression will occur when this end also has 0 velocity. Because the moment the block comes into contact with this end of the spring will start to get compressed. The block will have certain velocity, therefore the block will have certain displacement to the right, and therefore it will compress the spring further. It will keep on compressing the spring until the spring reaches its maximum compression. Maximum compression का मतलब ये हुआ कि अब और वो spring compress नहीं होएगा. इसका मतलब कि ये ब्लॉक अब और राइट मूव नहीं करेगा. इसका मतलब कि ब्लॉक की वेलोसिटी वहां पे जीरो हो गई है। अगर ये एंड ऑफ द स्प्रिंग मूव कर रहा होता तो मैक्सिमम कंप्रेशन की कंडीशन होती कि ये वाले पॉइंट की वेलोसिटी और ये वाले पॉइंट की वेलोसिटी, ये वाले पॉइंट की वेलोसिटी और ये वाले पॉइंट की वेलोसिटी सेम हो जाए। लेकिन चूंकि यहाँ पे इसकी वेलोसिटी जीरो है, ये वाले एंड की स्प्रिंग की, ये वाले एंड की भी वेलोसिटी जीरो होनी चाहिए। Okay, so let's put everything in. Minus half kx square is equal to final kinetic energy minus initial kinetic energy, right? माइनस माइनस कैंसिल हो गया। हमको निकालना है x। x की वैल्यू आती है हमारे पास m v नॉट स्क्वायर बाई k। This is the maximum chunk. So please take a screenshot. Please take a screenshot. कि ऊपर नीचे नहीं गया था विषय, ऊपर नीचे जा रहा है क्या लास्ट उसमें ऊपर नीचे गया। That is why. लिखना चाहिए था मेरे को, right? And that's a good observation. I should have written work done by gravity is, क्योंकि gravitational force तो act कर ही रही है उसमें। क्यों भाई भावे ऊपर देखो, क्वेश्चन पढ़ो ध्यान से। मैंने मैंने कोई वर्ड फालतू का नहीं लिखा है, मुझे उतनी हिम्मत नहीं है लिखने की। गलत आंसर है सर। गलत आंसर है सोनल। गलत आंसर है सुदीप। गलत। चलो देखो, नहीं गलत हो, इसलिए मैं बोल रहा था ध्यान दो जो मैं कर रहा हूँ। फाइनल, इनिशियल, फाइनल, and let this distance be x. So the path followed by the block is from here to here. Summation W, work done by earth plus work done by spring. Work done by normal reaction 0 रहेगा। हाँ, तो समझ में आ रहा है क्या गड़बड़ हुई है, कहाँ पे गलती हुई है? What is the work done by earth? What is the work done by earth? mgh नहीं है, नहीं प्लस माइनस mgh अतर्व क्या हो गया तेरे को? वेदांत ऊपर जा रहा है कि नीचे आ रहा है वो? हाँ जोहेब सही आंसर। गलत है राधिका। Look at the initial position, look at the final position, look look at the initial, look at the final position. What is the vertical distance between the initial and final position? Uh, Work done by Earth will be equal to plus mgh plus x. That is the whole point. Work done by spring is half k 0 square minus x square, because massless आइडियल पैन है ये. इसका मतलब स्प्रिंग का इनिशियल इलोंगेशन 0 होना चाहिए. इनिशियल काइनेटिक एनर्जी ब्लॉक की क्या है? ड्रॉप फ्रॉम रेस्ट 0. फाइनल काइनेटिक एनर्जी ब्लॉक की क्या होनी चाहिए? मैक्सिमम कंप्रेशन 0. Right, you get to see. I have not written anything which is extra. इसका कुछ मतलब है, इसका कुछ मतलब है, इसका कुछ मतलब है. All you have to learn is इनका मतलब होता क्या है. यहाँ पे आएगा mg h plus x minus half kx square is equal to 0. Work done by normal reaction क्या होता है? क्या बताया मैंने? Work done by normal reaction 0. Okay, I will not even bother to write. I will not even bother to write. नॉर्मल रिएक्शन और टेंशन की तो मैं बात ही नहीं करूंगा कभी भी. ये एक क्वाड्रेटिक इक्वेशन आएगा. इस क्वाड्रेटिक को सॉल्व जब आप करेंगे तो आपको मैक्सिमम कंप्रेशन मिल जाएगा. अरे तो सिर्फ क्या होता है? सिर्फ क्या होता है? अगली बार नहीं आना चाहिए. अगली बार नहीं आना चाहिए. राइट, that is the learning process ना. Now you know ना कि अब अगली बार ये मिस्टेक कभी नहीं करेगा ना भाई. चलो, please start HCV now. At least try to complete the first 15-20 questions, and we will continue with this in the next class. Okay. हाँ, लेक्चर 1 अब आप आराम से कर सकते हो. आराम से पहले ये करना भाई मेरे, इसमें मत चिंता करो. चलो, आई विल गो नाउ. हाँ, सब करेंगे, सब करेंगे, अभी नहीं, धीरे धीरे. चलो गाइस, बाय 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 बाय. अरे